Good day, students. We're still in lesson 16. It's a long one. We're getting there. It's part G. Two-tailed tests. Every test we've run so far has either been a greater than test or a less than test. You read the problem. The context of the problem tells you what kind of test to run. So, if we think about the large vehicles in Cecil College parking lot, I had the thought that more than 44% of all the drivers prefer large vehicles. And when we said more than, that's a greater than test. Same thing with the college cheating. Let's test for more than 75% are cheaters at a particular college. Those are right-tailed tests because I'm shading up or to the right. The high school attendance one, where we wondered if there was a drop in perfect attendance, was a left-tailed test. We were shading left. We were looking for a decline in perfect attendance. The allergies with the Amish community, same thing. Do the Amish folks have a lower propensity to have allergies, or fewer or a smaller percentage of the population? Those are called left-tailed tests. Sometimes you're just testing for a difference. In the alternative hypothesis, you'll put the not equals to sign down there instead of greater than or less than. You read the problem. Nowhere in the problem does it say test for a decrease. Nowhere in the problem does it say test for an increase. It might say, has it changed? Or something similar. Not equals to test. Look for those context clues. Students always question, hey Coop, how do I know what kind of test to run? It's always in the paragraph description of the problem. It's there. Okay? So, little tip. I don't know if this is actually a tip, but more of like, here's why things are the way that they are. When we run a two-tailed test, and we're going to calculate that p-value, we actually shade both ways. Okay? And so I'll give you a tiny little picture here just to illustrate. If I was testing, say, p equals 0.5 versus not equals to 0.5. This is what the alternative hypothesis will start to look like. And you get your test statistic, which is a z, and for instance, you got 1.99 as your test statistic. Converted that data to a test statistic. When we shade, I will go from z positive 1.99, I'll be shading up. I will also shade down from z equals a negative 1.99 and down. So it's a two-tailed test. We're doubling the p-value. In one way, you can think of it as a penalty. Before the test, you weren't sure. Am I testing for greater than or less than? I don't know. I'll just look for a difference. If you're looking for a difference, you need more evidence. You need to be further out in the tails, because once you double up the p-value, it's going to crank up that p-value to a bigger value, which means it will be harder to reject the null. So, in a nutshell, when you test a not equals to, you need more evidence to reject. Okay? So, and it's an easy fix. We're getting good at hypothesis testing. All right, example then. 15 years ago at Cecil College, let's just say that 30% of our students were on some sort of financial aid. We'd like to see if that proportion has changed. Here's the context clue from the paragraph. We're looking for a change. It tells me to run a not equals to test. We'll take a random sample of registration records, and we learn that 53 out of the 150 students currently are on financial aid. Is this evidence of a real change in the trend? Okay, so we're going to run the test. I'll flip over here to part A. Run the two-tailed hypothesis test, showing all steps. Notice we're not walking you through like part A, check the conditions, part B, write down the hypotheses, part C, calculate the test statistic. Now we're at the point in the course where run the test, do all the steps. We're expecting you to be able to do that. All right. Now, for this problem, we did collect some data, so I always like to just say, hey, what's the data? And I would summarize that with the sample proportion. And so p hat was 53 out of 150, I think. I better get this paper here. Yeah, and so that was 0.353. Remember, in the past, 30% of students are on financial aid. This year, I have 53 out of 150, it's 35% roughly. Think to yourself, does that convince you there's a change? This is certainly about 5% away from 30%. Is that strong enough evidence to change your mind for the whole school? All right. Let's write our hypotheses. H sub 0 for the null, P equals 0.30. And in parentheses, in my head, here's what I'm thinking. I'm going to still assume it's 30% to start. Let the data change my mind. Okay, so alternative hypothesis, P not equals 2 tests. It's our first one. Remember, we're looking for a change. Okay? In the essence of time, let's just say the conditions. As a student, you could easily write these down. The variable is categorical. Either you're on financial aid or you're not. We're going to presume this is a random or at least unbiased sample of 150, and the problem said that. 150 is certainly less than 10% of our population here at Cecil College. It's 2,500 to 3,000 students here. And do I have 10 successes and 10 failures? I certainly have 10 successes. I've got 53. And I certainly have 10 failures because I guess that means there's, 97 students not on aid. So 97 above 10. The conditions are met. You can use the formulas to get the test statistic for this problem. You can use the formulas and shade under a normal model to get that p-value. Possibly by this time in class, might be using StatCrunch to arrive at these values, and so if you know that method at this point, then do that. All right, let's see here. Test statistic, we're running a z-test. So z equals 1.42. Okay, so that's saying that the p-hat, the 35.3%, is about 1.42 standard deviations above the 30%. Not quite unusual, right? So, all right. Here's the p-value. I'll give you the value here and then maybe flip the page. There's some more room to write. The p-value turns out to be 0.156. And we've done enough tests where we say, you know what, that's just not low enough for us to reject the null. And we'll write all this up on the next page. But I'm going to erase this. I'd like to draw a diagram of this p-value and show you the shading in both directions. Okay, so I'm going to not flip the slide, but I'm going to flip the page. And let's see here. Make a little bit of space. All right, so we've converted to a z-score. Here's that standard normal model centered at 0. Remember what our test statistic was. It was a z of 1.42 on the back. Yeah, 1.42. Okay. Roughly here, z equals positive 1.42. Two-tailed test. Here's the shading up part. I go to the same number on the negative side, would be about there. Here's the z equals negative 1.42. And those two areas together are the p-value, right? So this is the p-value. What? I need to add together the stuff on the left tail. If you run the test using the StatCrunch capabilities, maybe we've done that in class, this is what we'd be doing. If you use the StatCrunch normal model tool to draw a normal model and shade, this is what it would look like. Little trick, if you are going through all the steps, you can find just the top area. And we know for sure that the bottom area is exactly the same as the top. So just find 1 and multiply by 2, right? Double it up. And you'll get that p-value altogether, 0.156. All right, we still need to reject or fail to reject definitely fail to reject. This is bigger than 0.05, it's bigger than 0.10, and so since that p-value exceeds, I'll say 0.05. Let me just squeeze this on the lighted area. Learn from experience, the video doesn't pick anything up too good over there. Since that p-value exceeds 0.05, which in my head is really when I start to think about rejecting, this is clear-cut fail to reject. This is clear-cut fail to reject H sub 0. If you flip back to, I think it's maybe video 16B in the notes, we have the p-value diagram. One could say this is very, very weak evidence for the alternative, but I'm not changing my mind based on very weak evidence. So fail to reject, and what do we conclude? We would conclude that at Cecil College, there is no real evidence. There's no evidence. The percentage of students on aid has changed from 30%. At Cecil College, there is no evidence that the percentage of students on aid has changed from 30%. So, our sample data was what, 35.3%, just not unusual enough to convince me to change my mind, and it really shouldn't convince you to change your mind either. All right. What we're moving towards, maybe you've recognized the parallels, but a confidence interval was the previous lesson. Hypothesis testing is this lesson. It's built on the same ideas. So let's go to part B. Support your conclusion with a 95% confidence interval for the true proportion of all Cecil students receiving financial aid. Comment. Now, perhaps in class we've used StatCrunch to sort of generate our confidence intervals at this point. Confidence interval, here's the formula, p hat plus or minus that z number times the big square root, p hat 1 minus p hat all over n. This point in the course, you should be able to do this. This is the 35.3%. We're doing a 95% interval. The z number would be what? Too slow, 1.96. And our sample size was 150. All right, students, you should verify. This would give me the interval. It's about 0.2765 and up to 0.4295. Pretty wide interval if you think about it. It's about 15% wide. I guess that would make the margin of error roughly 7.5%, somewhere in there. Well, you know, one reason this interval is so wide is because the sample size is 150, and for proportions that's on the small side, believe it or not. So interpret this interval, right? We are 95% confident that between 27.65% and 42.95% of all Cecil College students are on aid. We're 95% confident that between 27.65% and 42.95% of all Cecil students are on aid. Make sure you can get these numbers. It's important. Make sure you can get those numbers. Think about the hypothesis test. What did we conclude? No evidence to say it's changed from 30. What number is inside of that confidence interval? 30%, right? And so think about this. Since that 30% is inside the interval. It's okay that it's towards the lower boundary. Who cares? It's inside. Doesn't matter. It doesn't have to be right in the middle. Since that 30% is inside the interval, there's no evidence that it's changed here at Cecil College. What would need to happen to convince us of a change? Statistically, the whole interval would need to exceed 30%, or the whole interval would need to be below 30%. But 30%'s in there. Since 30% is inside the interval, again, same conclusion as our hypothesis test. There is no evidence that it's changed from 30%. In the next video, Kim Shepard is going to formalize this. You can actually run a test using a confidence interval. All right, a couple concluding remarks at the bottom. When you run a right-tailed test, you're shading rightwards, you're shading upwards. Greater than. Always shade from your test statistic to the right. In almost all cases, your test statistic will already be up in that upper tail because you're looking for evidence of an increase. But what you have to look at is that alternative hypothesis, say p greater than, I'll just throw the 0.5 in there again. That's a right-tailed test that tells me to shade right. When you run a left-tailed test, always shade to the left. Obviously, right? And when you run a two-tailed test, a not equals to, shade both ways to get that p-value. Like I mentioned a few minutes ago, shade from the positive value test statistic and up for a two-tailed test. Shade from the negative value test statistic and down. It would be the same number, just positive, negative. Or the shortcut, if you're doing this by hand, just find one tail and you can double it. All right, so we're getting good at these hypothesis tests. We just keep adding maybe one more layer every video, one little extra thing to think about. So make sure you ask questions if you need to. Thanks for watching, and we'll see you in class.